Hey, good afternoon, AP Calculus students. Mr. Ford here. It is actually exactly noon right now. This is 6.3.1 at the time of this recording, and we are doing all of these problems. There's only 6 of them here to do, and they're all pretty straightforward. Give us a good chance to practice a few things. So let's look at 685 first. We have to review the trigonometric Pythagorean identities listed below. As I've said many times, this is the only one you should ever memorize. The rest of them actually follow from that one. You get this one here if you divide everything by cosine, because sine divided by cosine is tangent, cosine divided by cosine is 1, and 1 over cosine is secant. And the same thing is true about this one over here. You get this one if you divide everything by sine, or sine squared, I guess. You get 1 cotangent and cosecant. Doesn't really matter for this problem, though. Question A is asking us to use one of these to write a new expression for sine of x. So how about we use the first one and just subtract the cosine squared and then take the square root. So how about the square root of 1 minus the cosine squared of x? I mean, honestly, that's all we really got to think about here. And that's how these are all going to work. The next one's equally easy. The tangent of x is just going to be the secant squared of x minus 1 and then the square root of that. Honestly, that's it. Plus and minus might want to go in front of these things just because of the square root nature of things. And the even easiest one, the expression for cotangent squared, all you got to do here is subtract 1 from both sides in this equation right there. So that the cotangent squared of x is going to equal the cosecant squared of x minus 1. And that's all, honestly, you really got to do here. 686, the next question. Examine the following derivatives. For part A, assume that y is a function of x, which we'll need to do because it's going to be an implicit derivative. Consider the multiple tools available for differentiation and the best strategy for each part. Evaluate each derivative and briefly describe your method. Okay, so let's take a look at A first. This is probably going to be the one that we spend the most time on in this section. d dx of 13x squared y. This is going to require the product rule because we have a 13x. Let's treat 13x squared as the first thing and y as the second thing. If you really want to break it down, which might be useful for this as an instructional example, the derivative of u is going to be 26x, and the derivative of v is going to be dy dx, since we do not know what y is, but we do know that it's a function of x. So putting all this together, the derivative of this is going to be, well, something along the lines of the following. You'll have the original first thing times the derivative of the second thing, plus the original second thing, y, times the derivative of the first thing, so 26xy. Honestly, that's as far as you really need to go with this because there's no, equals anything. That's it. So really, that is the derivative. Now, normally we would solve this for dy dx, but since there's no equal sign on the other side of this thing, we really can't do any manipulation with it. So, I mean, that's as far as you can go with this problem. Let's take a look at question B, which is the tangent inverse of 2 to the x. Now, if you have the formula that we wrote down from the end of class today, somewhere handy, or if you just Google, honestly, Google the derivative of inverse tangent, what we know is the derivative of the tangent inverse of x is 1 over, I'm gonna check my notes really quick, make sure I don't get this wrong. Again, I'm not a big fan of memorizing things. I believe what we wrote down was 1 over 1 plus x squared. Yes, correct. The derivative of the arctangent of x, or the arctangent of u, is 1 over 1 plus u squared times du, because remember we have to take the antiderivative. So you can skip a lot of work in this problem if you know what that derivative is. In this case, it's 1 plus x squared on the bottom of that. So honestly, if you are good to go with this, you can skip straight to the end of this problem. But I am going to work through this one as if we did it as part of our regular work today. So let's go ahead and think about a right triangle here whose tangent is 2 to the x over 1. That means that the third side of the thing is going to be 1 squared plus 2x squared equals the hypotenuse squared. And so the hypotenuse will be the square root of 1 plus 2 to the 2x power. Like that. That's kind of small, but They try to make it a little bigger there without making it bulky. So if we go through and do this as a, let's say this equals y, or something like that, like this in here, what we can think about here is if we take the tangent of both sides, we know that the tangent of, the tangent will cancel out. We know that 2 to the x, let's see, I gotta think about this for a minute. Yeah, 2 to the tangent equals the tangent of y. And then if we take the derivative, I know that the natural log of 2 times 2 to the x is the derivative on the left, and the secant squared of y is on the right, times dy dx. It's the implicit differentiation. And then finally, if you do the division, dy dx is going to be the natural log of 2 times 2 to the x, which is the derivative of 2 to the x. And that's all going to be divided by the secant squared of y. So in this case, the secant of y, which is the the hypotenuse over the adjacent, is just the square root of 1 plus 2 to the 2x power, like that. And if we square that, we square this square root, what will happen is the square root will cancel out. So our final answer is going to look something like this. Natural log of 2 times 2 to the x over 1 plus 2 to the 2x power. And that is what you would get if you had used this method up here also up top. You would just need to remember to multiply by the derivative of 2 to the x, because that's a chain rule. You would need the 2 to the x power derivative on the top of that fraction too. So that's as simple as I can make it. There's an exponent rule thing going on there where 2 to the x squared, we see it right here, 2 to the x squared is 2 to the 2x power. We see that a couple times in this problem too. So you can use the formula, you can use this method, whatever works for you. Let's talk about question C, which is going to be another review question. Actually, we can do question C right here in this space. It will not take too much time. It is a chain rule problem. What you have here is the outside function is the e to the x, but the thing that is the exponent here is x squared minus 2x. Sometimes you'll see it called u. Sometimes you'll see it written this way. What we have is we have e to the u, where u is equal to x squared minus 2x. So the derivative of e to the u is e to the u. So we leave the original part alone, e to the x squared minus 2x. Then we multiply by the derivative, which in this case is 2x minus 2, and we call it a day. We walk away from this problem because that is done. You could do some more distributing if you wanted to, but let's move on. We're going to use calculators to evaluate all 5 of the integrals in 687. So I'm thinking that by doing this, we're going to see some patterns, and I think you'll see those happen right away. We're going to cleverly use our calculator to make this work as fast as possible, and we're going to see some patterns, I hope, along the way. Now, the first one we can go ahead and write down equals 1 because it's an integral from, it's 0. I always get that backwards. It's the integral from 1 to 1. So since the boundaries are the same, there's actually no area under that curve, so it's just 0. For the next one, our integral, we'll grab our function out of our calculator. We're doing the integral from 1 to 2 of 1 over x dx. And that will be this number, 0.6931. Like that, 0.6931. I suppose you could round, no, that's fine. The next one is the same problem, only the boundaries are now from 1 to 5. So let's go crazy. Put a 5 there. 1 to 5 of 1 over x dx. It's going to be 1.609. Sort of thinking, what is the point of this? As a teacher, I'm thinking, okay, what's the purpose of this? For question D, we have 1 to the 1/2. Now, we should know that's going to be a negative number, probably, because it's going to flip the order around of our integral, but it's still the same integrand, 1 over x dx. So this time it's going to be, negative. It's actually the same answer we had for this problem, for part B, but it's the negative version of that. It's negative 0.6931. And the last question, I'm willing to bet, is going to be 1. I think this is probably what we're supposed to see here, because what we're previewing in this problem is the idea that the derivative of the natural log of x is going to equal 1 over x. And we'll see this. Yeah, it is 1. It's the last derivative formula that we need to learn. Is the derivative, I'm just going to write it down here. The derivative of the natural log of x is equal to 1 over x. And we're seeing it here that the antiderivative of 1 over x is the natural log of these numbers then. So let's take a look. Furthering that idea, let's take a look at the next question, which is 88. What do you notice about the area under 1 over x from 1 to any positive number as it relates to the natural logarithm? And why was the area negative in part D? So I'm guessing, let's just try a couple things on the calculator. I'm willing to bet that for question B, let's take a look at question B, which is this one right here. I'm willing to bet that the natural log of 2 is just that, is that number right there, which it is. So this problem is the natural log of 2. This problem, I'm willing to bet, I bet that's the natural log of 5. It is. It's natural log of 5. This problem is going to be negative because the order of the integrands is different. I'm guessing this is the natural log of 1/2. Which it is. And then finally, of course, this would make sense because the natural log of e is equal to 1 because that's a log base e of itself, which is always equal to 1. So what's going on here is we're seeing this. If we want to make a generalization out of this problem, this is meant to preview the last derivative that we need to learn. But I would say that the integral from 1 to a of 1 over x dx is equal to the natural log of a. That seems to be the pattern that we are meant to see out of this problem, I think. I don't know if it's super obvious. I don't know if I assigned that problem to you on your own and didn't walk you through it. I'm not sure it would pop up because I know natural logs are not a thing that the high school mind tends to go to right away on things. So I'm gladly here to guide you through that process and let you see that. Let's look at 89 for a moment here. We have 2 more questions to tackle, and neither one of them is too terrible. We're going to sketch the graph of y equals 2 to the x and its inverse and label all the intercepts. We'll start there. We're going to do this off to the side a little bit. We're going to think about the graph of 2 to the x power, an exponential function, which you might remember from your Algebra 1 days or beyond, your Algebra 2 days. 2 to the x power, which I'm going to graph in blue here. I know that like all exponentials, it crosses at 0, 1. That's the first point that I know. I know that after that, it doubles every time. So 1 goes to 2. Oops, I should just put a point right there. 2 is going to go to 4, and so on. It'll be a nice exponential curve going up this way and coming down this way. Exponential functions will never touch the x-axis. As you can see, they're just going to do that right there. I'm trying to make this graph as cool as possible. Now, as far as its inverse goes, the inverse of 2 to the x is the log base 2 of x. Like that. An easy way to graph an inverse is to take any set of coordinates on this graph. If there is an xy pair that makes this equation true, then the y and x reversed will make the second equation true. That's kind of how inverses work. So here's the thing. I know that log base 2 of 1, for example, well, hang on. How about this? The log base 2 of 2 equals 1. So I know that the point 2, 1 is on this graph. I also know that the log base 2 of 1 equals 0. I also know that logarithms never go negative. You can never, well, basically a logarithm is asking the question 2 to what power gives you the number in question. So there is no way to get a negative number out of that. So I know the graph kind of looks like this. And then it goes up like this. And it does increase forever in this direction, but it does look like that. You could use Desmos for this or a graphing calculator. If you're not super up on your logarithm graphs, it's going to look something like that. You know what, let me use the red color anyway, since I'm trying to color code everything here on this problem. Like that. Log base 2 of x looks like that. Another rule of logarithms is that you can always reflect them over the line y equals x. Or sorry, did I say logarithms? Inverses. Inverse functions always reflect over the line y equals x. Like that. Inverse functions are one last little derivative thing we got to talk about also. So we'll keep going forward with that as we head first. Let's actually answer some questions here. Question A asks us to write the equation of a line tangent to the graph of y equals 2 to the x at its y-intercept. Its y-intercept, of course, is the point 0, 1. So for question A, the point in question is 0, 1. So if we're going to write the equation, well, let's start with y minus y1 equals the slope f prime of x times x minus 0. If we're using the old point slope form that we use for writing the equation of tangent lines. The only thing we don't know is what the slope is there, although a pretty fair guess would be something like 1. Let's find out. The original function in this case is equal to 2 to the x power, so the derivative of that, f prime of x, would be the natural log of 2 times 2 to the x power, and the derivative when x is 0 is the natural log of 2 times 2 to the 0 power. 2 to the 0 power is just 1, so the derivative here, or the slope, is the natural log of 2. So by moving some things around, our equation of the line is going to look like this. It's going to be y equals natural log of 2 times x plus 1. That's it. It's going to have a slope of the natural log of 2 and a y-intercept of 1. In fact, now is a good time for us to probably go to the graphing calculator for a moment and take a look at what we got here. We have 2 to the x power, and we have the log base 2. I guess log base is somewhere in here. Let me find it here. It's in here somewhere. There it is. Inside of the math menu, let me walk through my keystrokes there. If I push the math button, and I go all the way down into the letters, right there, option A is log base, which lets you put any base you want there, which is nice, log base 2 of x. And while we're here, let's go ahead and graph natural log of 2 times x plus 1. And I want to, I should have made the window, the more natural window here. I just want to see what's going to go on. There's going to be here's our logarithm graph right there. You can see that the graph does kind of match what we drew in the previous problem. And there's your tangent line, which does intersect 0, 1 and is a slope. I'm going to make this the nice standard window that we've got here. So again, there's your exponential. Here's your logarithmic function. And here comes the line, and it's going to go bam. I love when that happens. It's so satisfying. So cool. All right, so we've answered question A. We've got the line there. Question B is going to ask us to write the equation of a line tangent to the graph of the log base 2 of x at its intercept. So we got to do some thinking with this one here. At its x-intercept, we should be careful there. The x-intercept of that graph is the point 1, 0. That is the point where this graph crosses the x-axis. So let's do some thinking here on this question. We know that we're talking about the point 1, 0. So if we're going to put our point-slope form together, it's going to be y minus 0 equals the derivative, or the slope of the tangent line, times x minus 1. Now this is going to be kind of tricky because the question is going to be, how do we get the slope of that line to happen? Because currently, the function in this case is the log base 2 of x. And we really don't have a way of taking the derivative of this. Not really. I'm trying to think of other clever ways we can get around this. We could maybe do like an implicit derivative somewhere, some way, somehow. But we might just need to think cleverly about slope and how we represent it. For example, I'm pretty sure that if we just took the inverse of the slope here, or maybe the reciprocal of that slope, we could get the inverse slope to happen right there. In fact, I can tell you pretty confidently that whatever the slope of this line is going to be, it's going to be the same. Yeah, it's going to be the reciprocal. It would be the same, it'll be the reciprocal of the slope. So it'll be 1 over the natural log of 2. Let's try that. I think that f prime of 1 in this case, I think what's important here is it's going to be 1 over the other derivative at 0. So let's try 1 over natural log of 2. I'm not sure this is going to work, but I'm pretty sure it will. Again, we don't really have a way of taking the derivative of the log base 2 of x, and guess what? We won't in this class. We don't have any way of that. But I think what we're meant to see here is the inverse relationship is going to cause the slopes to have reciprocals of each other. So if we clean up, I'm just going to try it. Let's get rid of the minus 0. Let's replace the slope with 1 over natural log of 2 times x minus 1. And I'm just going to go to the calculator really quick and just graph this and see if it works. So that is for the slope 1 over the natural log of 2 times, in parentheses, x minus 1. I think this should work. I'm just going to watch it come through here. Come on, buddy. Oh, there she goes. Look at that. Beautiful. Amazing. So the slopes here, I'm going to put some notes on this page here. The slopes are reciprocals of each other. I suspect that might be one of the next questions. One is natural log of 2, the other one's 1 over natural log of 2. Interesting. It does work. You have a slope of a tangent line right there. Bam. It works. Pretty cool. Let's take a look at the rest of the questions here. Question C says to graph both these tangent lines, what's their relationship? Are they inverses of each other? I think they might be. Let me just try a thing really quick. This is for question C. If I start with this line here, y equals natural log of 2 times x plus 1. If I switch the variables, x equals natural log of 2 times y plus 1, using my colors to kind of keep track of what's going on. If I solve this for y, yeah, the first thing I do is subtract 1 from both sides. So x minus 1 is natural log of 2 times y. Yeah, and then I multiply both sides by 1 over natural log of 2. Yeah, this works. So y is equal to 1 over the natural log of 2 times x minus 1. They are inverses of each other. That is the answer to that question. Which should kind of make sense because, each other. Because 2 to the x and log base 2 of x, these guys are inverses. So it should make sense that the equation of their tangent lines at 0, 1 and 1, 0 are inverses of each other. So that kind of makes sense. They're inverses of each other. I kind of like that answer. Question D says use the tangent line in part A to approximate the value of y when x is 0.1. Is your estimate an underestimate or an overestimate? Okay, so let's go back to question A for a minute. We had this equation right there. Let's call this part D over here. So we know that the equation is y equals natural log of 2 times x plus 1. So we are asked to approximate what's going on when x is 0.1 right there. So we're going to plug in x equals 0.1. The thinking here, of course, is that this is a very, very curvy line. But if you zoom very, very, very close in, you can tell there is going to be a local linearity. For a little bit of time, from maybe here to here, the graph is pretty linear if you zoom far enough into it. So let's just use that linearity to kind of check what's going on right around 0. How about at 0.1? That's the thinking. So this would be the natural log of 2 times 0.1 plus 1. Usually you see these in problems where you don't need a calculator, but in this case we are going to need one. The natural log of 2 times 0.1 plus 1 is this number. It's about 1.069. That's good enough, like that. And of course, as far as the over-underestimate question, this is going to be an underestimation because this tangent line here is always underneath the curve. So it's always going to be an underestimation. Another way to say that is because the graph is 2 to the x is concave up, always. If it's concave up, then its tangent line will always be underneath the graph all the time. Concave up. Let's take a look at one last question here. I think it's going to be very similar. 690 is going to ask us to consider the function f of x equals negative 3 to the x power. We're going to write the equation of the line tangent to that at x equals 0. So very similar. The first thing we should do is figure out, we need all the parts here. We know that x is 0. We're going to need to know what f of 0 is in the original function. And thankfully that is also 1, negative 3 to the 0 power, which is 1. And we're also going to need f prime of 1. So f prime of x in this problem is going to be the negative natural log of 3 times 3 to the x power. And so f prime of 0 is going to be the negative natural log of 3. Because once again, 3 to the 0 power becomes 1. Now that we have all these parts done, we can easily write the equation of that. It'll something like this. It'll look like y minus 1, again, that's the y value there, equals the slope, which is the negative natural log of 3, times x minus 0. Just using good old point slope form to put the parts in place right there. And so we can probably simplify this quite a bit. Y is negative natural log of 3x plus 1. How about that? We could check this on a calculator, but this video is already 25 minutes long, so let's just keep going. Question B says to approximate x equals 0.1 using our answer to part A. So very similar to what we just did. This is for part B. we're just going to take our tangent line, y equals negative natural log of 3 plus 1, and we're going to evaluate that. Negative natural log 3x plus 1. Let me clean that up. And we're going to check this when x is equal to 0.1. So we'll use a calculator for that because I don't think we have a way of evaluating logarithms without a calculator. Negative natural log of 3 times 0.1 plus 1. It's going to be about 0.89. Now, as far as question C goes, is that an underestimate or an overestimate? Without graphing, it's really kind of tough to see. The question is going to be, is this concave up or concave down, negative 3 to the x power? What that graph is, if you think about the graph of it, it's going to be a negative exponential. It's going to look something like this when you graph it. It's because the negative sign is at the end of the problem, so you do your 3 to the x power and then make it negative. So that means it takes the entire exponential graph and flips it down over the y-axis. This is concave down. So a tangent line at x equals 0 would look something like this, and you can see that it would always be over the line. So this is going to be an overestimate. And my explanation is because f of x is always concave down, like that, which causes that to happen. Pretty cool. Hey, we have one more derivative to look at in 632, and that's natural log of x, and I'm really excited about it because it's a really easy derivative, and you guys are going to have a lot of fun with it, and we're going to keep going. You guys are doing a great job. We're going to get to the end of this thing. I'm confident about it. We're almost there. You guys are doing a great job. I will see you in the next video. Have a great weekend.